day 2, you should have, or I'm sorry, day 0, you have a penny. Day 1, you should have 2 pennies. Day 3, you should have 4 pennies.
Right.
So you should check it. You should try it for like t equals 3 and make sure that this works. So if you have a calculator, you can do that. It does work. I'll just say it that way but you're welcome to check. Now the dime is different.
Mm-hmm.
A couple things are different. What are you starting with the dime?
0.10.
Okay, it's still doubling, so that means your A is still 2.
Right.
But it's every 5 days. And this is where it's probably very unclear. You divide the time by the doubling period. Now, why does that work? Because when t is 5, t divided by 5 is 1. When t is 10, 10 divided by 5 is 2.
Right.
And when t is like 15, 15 divided by 5 is 3. So that is why it works.
Okay.
Okay. Any idea how this plays out?
I think the penny would get more money.
It does. It does. One way is to graph this. Is that okay? Can I graph this for us?
Yeah.
Is that reasonable? Okay. Let me see if I've got that up. I do. Already got a graph up. Okay, so let me go to the graphing thing here. And we're just going to graph these things. 0.01 times 2 to the power of x. And then 0.1, 2 to the power of x over 5. Okay. And you're not seeing much here because I've got a bad window. So let's look at it over 30 days and see if we notice anything for this. Let's go 0 to, I don't know, $1 on the Y. Okay, so this is enough to sort of illustrate it. So they intersect after about 4 days.
Oh yeah,
Okay.
I see that.
Okay, but on the 5th day, the penny, which is the purple one, you have 32 cents. On the 5th day, you have the dime, only 20 cents. So you can see how quickly it yeah. Is that enough for this to show a quick graph like this? Okay, so let me snip that in the other screen. You share. Okay, so this is time in days on the x-axis. This is dollars on the y. This one is the penny. This one is the dime.
Okay.
Okay, so is that sufficient for that?
Yeah, it is.
Okay.
That helped a lot. Because I was doing the wrong formula. That's why I was getting stuck.
Yeah, you probably had the number inside parentheses, and it will go to 0 pretty quick. Okay, so 4 is really an interesting question, because what matters, we got to go grab the 2 equations again. 0.01 2 to the t versus 0.1 2 to the t over 5. The doubling time always matters. I'm sorry, this doesn't refer to the one we did. Oh, it does. It's interesting. The doubling time doesn't matter. You could actually put any amount you want here in the dime, and the penny will always grow faster than it at some point.
Right.
Which does maybe okay, so that's one way to see it, but The other way, the math way here, is that you can actually break this thing apart. So this becomes 0.1 times 2. It's really 1/5 times t as your exponent.
Mhm.
And then you can apply the 1/5 to the 2. So it's 2 to the 1/5 power to the power of t,
Mhm.
0.1 here. And so what I'm trying to show you is that it's really similar to this one on the left, 0.01 times 2 to the t. But now the inside number, the 2 and 2 to the 1/5, you're comparing those two numbers.
I
Okay,
see.
so the fifth root, or 2 to the 1/5 power, it's not very large. It's 1.15. So this is really 1.15 to the power of t versus 2 to the t. So it doesn't really matter what you start with, because this 2 is better than the 1.15.
Okay. I see what you're saying.
So any words that sort of say that, plus any sort of what I've got here, will probably be sufficient for you to get full credit for this. And how are you doing in this class? Is your grade good? Are you things
So far,
okay?
my grade is good.
Good to hear.
So doing good on it.
Okay, there's a lot here now that I'm looking through this. Okay.
Yeah, there's some that are, it's like one and then the one below it is just like it. I just like, if you do one, I'll kind of copy your steps for the first one and do that one.
Sure. Yeah, sure. That
I,
sounds good.
I just need the help to do that one so I can,
Yes.
be able to do that process.
So it looks like 5C is next. Is that right?
Yes.
Okay. All right. And you were supposed to make this modification where you adjust the year to 1980 is year one. Is that right? Yeah. So
Yeah.
this is so really this is, it's easy for me to do this because I can just overlay, but it's 2, 3, 4, 5, 6, 7, 8, 9, 10.
Yeah.
Right. Okay. So here's what I'm going to do. I'm going to go back to Desmos. I'm going to graph it so I can snip that in for you. Is that okay?
Yeah, that'd be
All
great.
right. All right. So let me go do that. Where did it go?
My teacher chose something very depressing to be his example.
Oh yeah, a lot of these are not ideal. Like that. So let me get a new window here. So what I really like is it's going to give us the dots there. A lot of times they just reuse whatever they had from the previous semester and don't give you current stuff. 14.7. Label 6, 13.2, 7, 12.8, 8, 12.2, 9, 9, 12.8, and then 10, 11.6. Okay, and I'll come back and hit the label on all these. All right, so let me affect the window here. Let's make this window a little tighter. 0 to 15, 0 to maybe 20. I don't know, something like that. You're gonna have to decide, increments and stuff, but this has a general trend down. Hopefully you can see
Yeah,
that. It's got a
this one.
general trend down, and then we do need that. I'm gonna let me do this something else here. I do need to show it without the labels, and then I'm gonna jump back to the screen.
Mhm.
It'll help us with drawing a line of best fit. Okay, so let me go to the other screen here. All right. So I got both graphs here. You're seeing the one without the labels, the one with the labels. So you can have that later if you need it. To me, it looks like it's going down and to the right. So the next thing they're asking is to describe the graph in words. So they're looking, when the person's grading this, they're looking for certain words here, like it's slope is negative.
Oh,
Okay, you might want to say that it's decreasing over time, but you want to be more specific than that. You want to say, well, what is it that's decreasing? It's the infant mortality. Infant mortality is decreasing. It's decreasing over time, and that's a good thing. It's much higher in other parts of the world. So that's a good thing. Now, the next thing it says is to choose any two of your data points and label them A and B. Let me look ahead here.
this one's kind of the longer one. It takes up like 3 pages.
Yeah, that's okay. So we're gonna draw a line of best fit here, but we want to pick nice points if at all possible.
Mhm.
And it's hard to know what is a nice point. Like this kind of looks like a line of best fit. That's a little. So we're looking for like the same number of points above and below it. I don't know, maybe something like that.
Right.
That's kind of our line of best fit here, but they want you to pick 2 points. Let me go back and look at the table and see if I can pick 2 nice ones that will work for us. Let's see, 2.2 divided by 4, 2.8 divided by 5, 3.4 divided by. Okay, so let's use the following points for A and B. Let's go 3, 15,
Yep.
and then 5, 12.2. Okay, so that's part D.
Right. I see.
So to find the slope in part E, we use the slope formula: y2 minus y1, x2 minus x1, 12.2 minus 15 over 5 minus 3. Wait, I'm sorry, hang on. Maybe make sure I gave you the right points there. No, I gave you, this is 8. Sorry, 8. 12.2. I was looking at the wrong year. So this becomes minus 2.8 over 5. Okay, so this becomes minus 0.56. That's about as nice as we can get it for your slope. Sometimes when we want oh, there it is, interpret the slope. Okay, there it is. All right.
Minus 256?
0.56.
0.56, sorry.
Yes, yes. Is my screen showing? I'm showing the
Yeah, no,
yeah.
I thought I heard something that, I was like, wait a minute, I'm seeing something different than I thought I heard.
Is the audio quality okay, or is it choppy at all?
A little choppy, but not that bad.
Not bad. Okay. Okay, so now part E continues and asks you to interpret this number.
It's a number.
Yes, it is. So when it's negative, you say decreases
Okay.
by, and then you give the number 0.56, and then you give the units of the number, which is the infant mortality rate. mortality rate per year. There's one little more piece to this. I guess it gives it to you in like thousands. Thousands live births. So we should add that in here. 0.56 thousands per live birth. We could multiply the two, but I think that's okay for now.
Okay.
Okay, part F is to write the full equation. So we're going to use this equation: y minus y1 equals slope x minus x1. And the reason we're going to use that is because you have a slope. That's the one you just calculated. And we're going to use one of the points that you calculated. We're going to use A, 315. So this is x1 and this is y1 here. So we have y minus 15 equals minus 0.56 x minus 3. Okay, so we need to solve for y. So you have y minus 15 equals minus 0.56 times x. You're going to distribute that minus 0.56 into both. So minus 0.56 times 3 is minus 1.68. And then you're going to add 15 to both sides. And that's the final answer for part F.
Okay.
So we're up to part G.
Yes.
All right, so for part G, it says to use your equation to estimate these values. So for each year, we have to convert it from the base year. So the base year was 1980, and you're going to subtract each of these from 1980. So that becomes 12, 15, and 19. Okay, and you're going to use the equation you just found. It's really x, not t. I get it. Maybe they wanted x. I don't remember. But we're going to put that in. So it's minus 0.56 times 12 plus 13.32. So if you have a calculator handy, please double check these. Looks like 6.6 for that. And then 2.68. Is that consistent with what you have? Okay. So it should be going down, and that's what the model, that's what the graph showed. Better healthcare, more awareness, all that stuff probably contributes, but that's a different class. This is just what do the numbers tell us here? Okay, so here is part H.
Okay.
What is the y-intercept of your equation? So we already answered that. It's the 13.32. Okay, and then the interpret is always write a sentence. So in the base year is 1980. There are 13.32 thousands infant deaths per year, or thousands of infant deaths.
Okay.
Now it looks a little high. It's okay. I'm just trying to decide if yeah. All right. So what's the next question here? It asks, does it fit the data points? It's a little high. Excuse me, if I go back and look. So let me go back and grab that graph. So we're plotting that equation, the 13, the minus 0.56 x plus 13.32. We're kind of it's here. It's a little flatter. It's kind of like more like that.
Oh, okay.
It's not a great fit. It does bother me a little bit. Let me just go back and check these numbers.
Okay.
Because it really should have, I mean, really should have a, okay, let me just make sure these are right. 3 and 15. That's 1983. And then 1988, 12.2. So that minus that minus that. That looks right to me. I don't know if you checked this or not.
I'm checking it right now. No, that's what I got.
Okay, so I think you're getting a little bit of flexibility here on where it goes. I mean, maybe we didn't pick the best 2 points, 315, 812.2.
It's true, they gave us freedom of choice on that.
That's right. So I used that point and that point,
Okay.
but that still isn't, there still is something that's not right here. I apologize. Okay, here it is. Here it is. This is the issue. This should have been a plus. That's the issue. I'm so sorry. And that does affect everything else we did from here. 16.68. So the reason is the two negatives make a positive. That's why this is positive.
Yeah, we should see.
Okay, and that's going to change all of these numbers. So we're gonna fix that. And then that does change the graph. But this is all for the good, because we want the right answer here. We don't want to submit work that's wrong.
True.
This is 9.96. This is 8.28. $6.04. Okay, and that changes this one right here. It's 16.68 is the y-intercept, 16.68 thousands, and that changes your graph as well. It's more, now it looks a lot better.
Oh yeah, that looks like it makes more sense than the
Yes.
one that wasn't really touching any of them.
Yes. So I think that takes care of that. Now, does it appear to fit the data? Yes. You want to say that the how do I want to say this? Explain. So kind of a good estimate is saying about half the points are above and below the line. You could also say that it follows the data, like the trend is down.
Right.
any of those words should be satisfactory for this.
Okay. To explain.
Let me know when you get all that down and we can move on to 6A.
I'm ready.
Okay. Okay, the following situation can be modeled by linear models. Find the equation modeled and then use it to answer it. Then briefly discuss whether linear model is reasonable for the situation described. All right. Okay, so 6A, it's a bunch of parts here. So part A is to write the equation.
Okay.
So for part A, let's use function notation here. So the price as a function of year X is the amount that it started with in the base year plus the amount that it goes up or down by each year.
Okay.
Okay, so that's like the first thing that's required in each of these. And then we want to evaluate it in 4.5 years. So that is $41,600. Okay, so now we can answer whether it's reasonable for the situation. That answer depends on whether you think prices go up, cars prices go up by the same amount each year. And I don't know. I don't know how to answer that. For a while they were a lot higher because supply was down.
Yeah, no kidding. It'd be
I think they're
easier to like example like why cars decrease.
cars. So if this is a new car, I mean, I'm probably reading too much into this, but like this wouldn't go on forever because then at some point it's really expensive for,
Right, it taps out.
yeah. So you can that's as far as I'm going to go on that problem.
Yeah, I get that.
Part B.
Okay.
Oh, and don't forget units. It should be dollars here.
Oh.
All right, a snowplow has a maximum speed of 40 miles per hour on a dry highway, no snow. Its maximum speed decreases by 1.1 miles per hour for every inch of snow that is on the highway. According to the model, at what snow depth will the plow be unable to move? Okay, so we're going to use we're going to say speed as a function of X here. And it starts out at 40. Decreases by means go down 1.1x. Okay. And if it's unable to move, that's when the function equals 0.
Right.
So we're setting 0 equal to 40 minus 1.1x. If you add the 1.1x to both sides and then divide by 1.1, x equals, we'll get that number here, about 36 inches-ish. That's a lot of snow.
There's a lot of snow. It's probably a good thing for your snowmobile not to break, not be able to move and
right. So I don't know, is this reasonable? It kind of depends on whether you would use a snow plow at this speed. Or that's so much snow, you probably are going pretty darn slow. I don't know. Again, I'm probably just overthinking these because I see this kind of stuff all day long, so I'm not sure what's reasonable sometimes.
Yeah. Okay. Turning to page 7.
7A, yeah. Usually they give you like one that's reasonable and then one that's unreasonable.
Usually that's how it works because they want you to be able
Right.
to tell the difference.
So I would say that the first one's probably reasonable, but the second one is not.
Yeah.
But you can object. I don't know for sure. All right, your dog weighs 2.5 pounds at birth and 15 pounds after 1 year. Based on those data points, find a linear function that describes how the weight varies with age. Use your model to predict the dog's weight at 5 and 10 years of age. Comment on the validity of your model. Okay, so we need two data points. Birth, so that's X, and then the Y is the weight, is 2.5. And then after 1 year, it's 15 pounds. So we're going to use this to find the slope. Y2 minus Y1, X2 minus X1, 15 minus 2.5 over 1 minus 0. All right, and then so this is 12.5 over 1. So this means that it grows 12.5 pounds per year. What do you think of that number?
I think that's a very fat dog.
It will be. It will certainly be a fat dog in 5 and 10 years. We know this is not true, but and that's why I was saying comment on the validity of the model. You'd want to say something like the growth charts in these things are, yeah, they grow quickly, but then they level off.
Right.
And same with humans, same with really anything, like you don't grow it forever. So now your function, we're going to start with y equals mx plus b. Your m is 12.5. Your b is what you started out with at birth, which is 2.5, like that. And then we're just going to switch to function notation because that's what they asked for in this. They asked for a linear function. All
Okay.
right. So now we can predict the weight in 5 years. F of 5 is 12.5 times 5 plus 2.5, which is 65 pounds, which is quite a bit for a dog that only weighed 2.5 pounds at birth. And then 12.5 times 10 plus 2.5 is 127.5 pounds.
That's, yeah, definitely unreasonable.
Yeah, definitely. So there is some relationship between the size of the dog and how long it lives. Like the larger dogs don't tend to live as long in general.
Right.
But um, that's depends on a lot of factors, right?
Mhm.
Okay, so that's A.
Yeah.
Going on to B, 12B. Okay, you can purchase Ford Focus for 16,500 or lease it for 3,000 down and 200 per month. Find a function that describes how the cost of the lease depends on time. How long can you lease the car before you've paid more than the purchase price?
I'm
Okay.
gonna say not very long.
Yeah, it's leasing is just below renting in terms of the actual numerical calculations about how
Mhm.
bad you're getting ripped off. Renting is the worst, but leasing is a close second. All right, so the cost of the car is what you start with. You have to put $3,000 down, and then you add to it $200 a month.
Right.
Okay, so that's your cost function. It's very, very straightforward. Something maybe we saw earlier. It's the fixed plus the variable
Right.
cost. Okay, and then at some point we want to know, well, when does this equal? We do that in the next line. When does this equal 16,500? And so, can you solve this for us for x?
Okay, yeah, x equals 13,300.
13 point something. What
Nope,
did you get?
13,300.
Okay, well, let's check that because that's a little bit too large here. So you're subtracting 3,000 from both sides.
Yeah, that's what I did.
200x equals 13,500.
Mhm.
Divide by 200.
Oh,
Okay, so
yeah,
so
yeah,
it's gonna be, it is the rough estimate, it's gonna be around 70 months. No lease goes that long. This is 67.5 months. So most leases are in the 2 to 3 year range,
right.
and they always have a lot of fine print, like you can't go over a certain number of miles, the car's got to be a certain price or a certain condition, and then they always give you a like they'll let you buy it at a certain amount when you're done with it.
Mm,
What's interesting about leasing, so this will be the last thing I say, is they do not disclose the APR or any of the other financials because they don't have to. Whereas when you purchase it or get a loan, they have to disclose that. That's why it's just above renting or just below renting,
right.
because they're really doing it for the benefit of themselves.
Mm,
All right, number 8, 8A,
yeah,
8A. Is this the
yeah,
last question? Oh no, 9 is. All right,
yeah, there's 9 also.
we'll see if we can get through both of them. It's gonna be really close. All right. So I mentioned this earlier. 1 plus R is for growth,
Mhm,
and then 1 minus R is for decay.
mhm.
And the R is the percent. Okay. So in your problem, R is 0.03. You never use percents. You always convert to decimals. And then the initial amount is the 135,000. So your function here is Q of T equals 135,000, 1.03. That's the 1 plus 0.03 becomes 1.03 to the power of T. So that's the first part. T is in years.
Okay.
Any questions on that?
Mm-mm.
Okay, so part B, we're going to use this equation. Let me snip that in. Part B is, what will the average price of a house be in 2020? So T is in years. We got to add a little more to it. It's since 2013.
So,
Since 2013. So this 2020 is not T. You have to subtract the base year out of it. So T is actually 7. So you're finding Q of 7 equals 135,000, 1.03 times 7. So this is 166,032.97.
got it.
Part C is for 2030. So T is now 17 years. Base year is 2013. So same thing, Q of 17, 135, 123, 1.03 to the power of 17. And $223,134.43.
Okay.
All right, so part D, they want to know when the house will be 190. 90,000. So that's Q. They're giving you the Q of X value, 135,000, 1.03 to the power of T. Have you guys covered logarithms in this class?
No.
Okay, so here's what I would do. I would graph these, and we'll do that here real quick so you can see how to do it. But I would just graph these. Like that would be the easiest way to do it. So let me go to the other screen and show you that. New share. Okay, so let me clear all these out. Okay, so we got y equals 190,000.
Mhm.
Y equals 135,000 times 1.03 to the power of X. We can't use T. And of course you can't see anything because the Y values are so large. Let's go 0 to 30 years. And we'll go 0 to, let's go 400,000. There we go. Okay. So now we can finally see where they intersect there. You can see it's at T equals 11.56 years.
Mhm.
And you might have to convert that. You might have to say, oh, that's really 2013 plus the 11.56. So it'd be sometime in like 2024. Does that make sense?
Yeah.
Okay, now for part E, I will go back to the screen, but for part E, we're just changing the Y value to 20,000.
Oh yeah. See that?
And so that one there is 16.52. Again, not the year though. So you'd have to convert that. You'd have to add that to 2013 and get a year for that. And then for part F, I'm writing this down as we go. For part
Mhm.
F, when will it double? So that's when the house price goes to 270,000. And we can similarly get that there. It takes about 23.45 years for it to double. All right, so I'm going to snip this in case you want to do this later and try to recreate it. Then I'll go back to the other window.
Okay.
All right, share screen. Okay, so like I said, the answer to D is 11.56 years, but you might have to convert it to an actual year. So 2024, 2025. Same thing with this one. It's 2029, 2030. But I would use that year, the base year.
Okay.
First one, and then same thing with the last one, 2013 plus the 23.45. So 2036, roughly 6.
Right.
All right. So 9A, this one's a decay function.
Minus.
We're gonna do 1 minus R in this one. So again, kind of a deceptive there. It's 1 minus R, 1 minus 0.15, which is 0.85. So your Q as a function of time is however much it started with, 12, 0.85 to the power of T. T is in hours. So let me quickly go through B. So B is to find Q of 4. C is to find Q of 12. D is to go 8 equals 12.85 to the power of T. So you can use the calculator for that.
Yeah.
And then for E, it half is 6. You can use the calculator for that. F. So this is maybe the hardest one. So let me really quickly do F on the other screen so you can see that. Okay, so 12.85 to the power of X So my graph is way off here. Let's go 0 to 24 hours and then 0 to 15. Okay, so here's what we're looking at. It said from 6 to 9. Is that right?
Yes, it
Check
did.
that's okay. So then x equals 6, x
Well,
equals 9.
6 to 3.
6
6 to 3.
oh, okay, grams. Okay, y equals 6. Oops. Y equals 6. Why is that happening? Y equals 6. Y equals 3. Okay, so these are the two intersection points, and you just want to subtract the x values there. So I'll snip that in, and that will do it for us for today.
Yep.
Okay, so sorry it was rushed here at the end. Let me go back to the other screen. But to do part F, let me know when you're seeing that.
Yes, sir.
To do part F, you take the 8.53 and subtract the 4.265, and that'll give you your answer.